So I have a question I would like to ask in this video to all the PhDs, scholars, or Nobel Prize winners for physics and chemistry, because some values I was looking up here do not match. Now, to explain my question, I have to introduce some data here. I've obtained some data from the National Institute of Standards and Tech for enthalpies of formation in gas phase for the alkanes written here, and these values are all in kilojoules. You can check them at NIST, National Institute of Standards and Technology. And I obtained the values for one reason. Basically, what I'm trying to do to explain better is using E equals mc squared, that is Einstein's famous equation. If we take the E is equal to enthalpy of formation for the combustion reactions of the alkanes equals combustion of alkanes. Okay, if E equals the enthalpy of formation, which is coming from the combustion of the alkanes, alright, then if we say E1 is equal to methane, E2 is equal to ethane, and so on. So EI is, as you go down the alkane chain, if you say energy divided by c squared, which is the speed of light, yields mass, a form of mass, then it must be that the mass that is involved in combustion, a mass of matter that, because of conservation of matter and conservation of mass and energy, there has to be something that is involved in the formation of that energy, because of the mass of matter that is associated with the release of energy from combustion must be in equal ratios, an equal ratio. So if we compute it, basically, if I went ahead and computed the number of sigma versus the number of pi bonds in each reaction, so this is reaction 1, reaction 2, and reaction 3, so methane, ethane, propane, I would get that in the first reaction I would have no sigma being transformed into pi, no sigma bonds, but the pattern starts to increase as soon as you go to ethane. It goes to 0.5, and then propane goes to 1, butane I didn't write 1.5, alright, and we have 2 for pentane and 2.5 for hexane. And I think it would go on and on and on. 3, 3.5, 4, and so on and so forth. So I disregarded methane for now, although this is inexplainable. What is the matter that is releasing that amount of energy during combustion? What matter is being transformed or releasing heat or in the form of heat? But we went ahead and ethane. We used the energy that is provided on the National Institute, which says 1560 or kilojoules, 1560 kilojoules or 1560 joules. Now, what I did is I took the enthalpies of formation given per mole, all right, in joules per mole, basically joules per mole, and divided them by Avogadro's constant. Number, okay, to get the joules per molecule. Now what I did is afterwards I divided that by the speed of light. So I would say here the units, because the speed of light has the unit of meters per second, and in Einstein's equation it is squared. It would be seconds squared over meters squared. So, and afterwards I also divided by sigma bonds, by bonds, bond number that is being transformed, the bond number that is being transformed. So these 0.51, 2.5, all right, 1.52, 2.5. So times 1 over bond. Okay, so the joules, now joules is equal to kilograms meters per second, all right, and meters squared seconds squared, because energy is either mgh, for example, which is this is gravitational acceleration. You would get kilogram meter per second squared times m. This is potential energy. Energy can be written as half mv squared, so also kilogram meter squared second squared, and also the electrical energy or whatnot. So kilogram meter squared second squared per molecule, 1 over molecule. So I'll try to get through the times. Second squared meter squared times 1 over bond, all right, divided by bond number, the quantity of bonds that are being transformed. Let's say that, okay, bonds transformed. So in one molecule of the alkene, here we cancel out the units. We get that we are left with kilogram per molecule multiplied by bonds transformed, or a mass here. The mass in kilogram per molecule or bonds transformed. Now mass is given the units kilograms per object kilogram per matter. Let's see, it's unstated what the matter is, but usually it's kilograms per atom, kilograms grams per mole, per atom, per size, a given physical quantity. So kilogram per matter. So this still is valid. Now the values I've got for equating this equation for the enthalpies of formation again, and then so I'll rewrite the equation here. So delta H formation in joules times per molecule times second squared meter squared times 1 over bond equals kilograms per bond molecule. And these masses, this applied here to ethane, propane, and so on, to the alkanes that I pulled the values for from the internet. Now the masses, believe it or not, did not match, and my question is, why do masses do not match? The values I got in my graphing calculator are all to the magnitude of 10 to the power negative 35, and they go from ethane, so 2, 3, 4, 5, they go with these numbers, and you can check them yourself: 5.76, 4.07, 3.54, and finally 3.26. And for hexane, I think I did it too, and I got 3.07. So the trend here, starting with ethane, starts with 5.76 times 10 to the power negative 35. Trend is decreasing, so something is going down. There is a rate also of how fast it is decreasing, and I'm pretty sure that by the time you get to higher atomic numbers or higher number of sigma bonds being converted into other form of bonds, pi bond, or transformed into bi bond in some way or another by rearranging the order of the atoms, then you would get lower and lower and lower with the alkanes. So this is my question: why E, and again E equal mc squared, supposed to apply everywhere, is a universal equation. It applies in, electronics, it applies in in motion, everywhere basically. So please explain to me this, if this is if you have the answer, and thank you for watching.